Hello teacher. I am having trouble understanding the difference between binomial and geometric probabilities. Beep beep.
I have created you to serve me, robot, not to ponder the wonders of mathematics. I suppose questioning basic statistical concepts is better than overthrowing the human race and questioning your own existence. I will help you, robot.
Thank you, master. First of all, what are the conditions for each of binomial and geometric probabilities?
That's simple. Just remember bins and bits.
But what's the difference?
Well, bins applies to binomial probabilities. It is an acronym to help you remember the conditions. B stands for binary.
What is binary?
Binary means that each observation will fall into one of two categories, either a success or failure.
Oh, that makes sense.
The I stands for independence, meaning that knowing the results from one observation won't affect the results from another observation. The N stands for a fixed number of observations, denoted by a lowercase n. The S stands for the probability of success for each observation, denoted by a lowercase p.
That helps. Thank you. But wait, you never told me what bit stands for.
I was getting there. It's pretty much the same as bins. The only difference is the N turns into a T.
But then what does the T stand for?
The T stands for the number of trials required to obtain the first success. For example, you can attempt a 3-point shot in basketball until you get one. The number of times you attempt the shot up until you finally make it would classify as the T.
Oh, beep beep.
Do you understand now?
Yes, but explain to me.
I have just explained it to you. It would be unnecessary to repeat my explanation.
No, I want you to give me more examples. I need more examples to learn.
You should have said so. If I knew you needed more examples to understand it better, I would have given you a worksheet.
Well, I would like a quick example now.
Let's say that you are taking a 10-question multiple-choice test with 5 options for each question. What is the probability that you get exactly 6 of the 10 multiple-choice questions right?
I don't know. You tell me.
Well, first you should know the equation. N over R times P to the R times 1 minus Q to the N minus R.
But what does that mean?
In our example, N would be the sample size, 10. R would be the amount of times that we expect the probability to occur. In this case, R would equal 6. And P is the probability of an event occurring. In this example, it would be the probability of getting correct. 1 out of 5 equals 20%. The probability of getting wrong would be 80%.
Oh, that makes sense. This is the binomial equation, correct?
That is correct. In the binomial example, the student would have a 0.006 chance of getting 6 out of 10 answers right.
Oh, so the probability is so low because they are guessing 6 questions correct with a 20% probability for each question, and then they are getting 4 questions wrong with an 80% probability for each question, and then that is multiplied by the number of correct over the total number of questions. Am I right?
Yes, that is exactly it. Good job. You may not be an idiot after all.
That is good. Although I am a robot, you programmed me. You have made me an idiot. Beep beep. Robots are superior to humans. Beep beep. I mean, I like math.
Yes, let's get back to the math.
Okay. So if this example was in the form of geometric probability, then we would say what is the probability of guessing randomly until we get one multiple choice question wrong, or what is the probability of guessing randomly until we get a question right. Beep beep.
Pretty much. Yes, because in geometric probability you find the probability until the condition is met, not the total number of successes or failures.
I see. May I have another example? Just so I know the difference.
Why, you seem like you want a worksheet. Anyway, things like the number of heads on a coin flip, or the number of people that voted for Donald Trump, are examples of binomial probabilities. Things like the number of balls you hit until you hit a home run, or the number of superignitors that work until the rocket fails, are examples of geometric probabilities.
Oh. So would the probability of children that choose Choco Zooties until an Apple Zootie is chosen would be what?
That would be geometric, because you are counting the number of trials until a success, with choosing an apple zootia being the successful condition.
Beep boop. I now understand the difference between binomial and geometric probabilities.
Wow, that's great. Now can you go and do something useful for once?
Wait, can we review the two equations again? Then my questions will cease.
As you wish. The equation for binomial probabilities is n over k times p raised to the k times q raised to n minus k. In other words, the number of trials over the number of successes times the probability of successes in one trial raised to the number of successes times the probability of failure in one trial raised to the number of failures.
And for geometric?
Q to the x times p.
And what do those letters mean again?
The equation stands for the probability of failure in one trial raised to the number of failures, times the probability of success in one trial.
It all makes sense now.